So we're almost halfway through already. Next week, halfway through next week will be the midpoint.
What's up?
Alba. Costa. Bauer. Booze. Chambers. Colvin. Gotcha. Farmer. Gotcha. Mr. Hallmark. Gotcha. Calabajou. Right. Mr. Jew. They're making horrible noises. Sycmatics. Got. Oh, that's on there. Mr. Moon. So Taro. Rodriguez. Sager. Sarita. Timber. Vargas. Got you. Vasquez over here. Mr. Wayne and Mr. West. Okay. All right, so let's see. Everybody got their homework turned in. You to turn back. A couple of you seem to struggle. We got out in the middle of this one. Jude has this whole turn it sideways thing going on. Okay.
That's the way I learned it.
That's the way your brain works. It is what it is. All right, guys.
Whoever's in copy, that's all right, because I know I can this one.
Yes. Over. X-Men. Our do bar slide. I did.
Thank you, I appreciate it.
Very first job I ever actually that's the second job I ever hired. It was a very effective job with bar slide. Long countertop. I was serving coffee, a brand new coffee pot. Brand new out of the box, just filled it up, turned and hadn't gotten the screw tight. As I turned, I didn't let go. The ball of coffee was just like a bowling ball. It just slid right down the counter. Hit a napkin holder, exploded. They had to fire someone. They had to fire someone. Augusta. Yeah. Okay, so let's take a look at let's take a look. The current iteration. So this one had five resistors in it, and it was woefully scant in information. Draw it out. 2, 3. And it looks like we had one doing a shortcut and another doing a shortcut here. Mr. Alva, do you have homework? 2, 3, 4, and 5. It's over here. So total. 5. Voltage, current, resistance, power. Okay. So we had some values. We had the voltage drop across 1. Then we were given some powers. 0.92062 watts, 0.58728 watts, 0.18189. That's what it seems like was probably a repeating thing. 0.73224, 0.08514. Watts, and watts. Okay, so that's all the data available. Got it? Homework? Okay, so not much to do on the analysis side at this point, is there? In terms of looking at the circuit, figuring out how we're going to do resistance. We don't have any resistance values, right? And in fact, it looks like there's only a couple of places where we can do any mathematics. So we've got one of our columns has 2 ingredients in it, and one of our rows has enough ingredients to solve for the total, right? So, and we know that the rule for power is a power user is a power user. The series and parallel, none of that's relevant. Each load uses X amount of power, consumes X amount of power. All we need to do is add them together. So in the case of solving here, all we need to do is straight addition, right? So we can add all of these up. For this one, because we have 2 ingredients, we can use several versions of Ohm's law to get current and to get resistance. Okay? If we do, one other presumption we can make that may or may not be accurate, but we can be looking for it. We know that R sub t is probably going to be some bizarre number, okay? With the parallels going on in there, etc., and the reciprocal formula, it's going to probably make some unusual number. However, the rest of the resistors, 1, 2, 3, 4, and 5, if they're very close to a preferred value, then like, 1, 15, 10, 1K, 39, 47, 56, right? Any one of those preferred values, 33 is another one. 22. Okay, if it's fairly close, or 2200 or 22,000, fairly close to one of those, we can pretty much just drop that number in there. So if it says 149.99999, probably 150. Okay, so we can do that. Otherwise, we kind of round it all the way out to the 5th decimal place in power. That's kind of a significant degree of precision. We can guess, just looking at this, that that's a pretty high resistance there, whatever that is, because it's not a lot of power being used. These in through here, so that one and that one combined just about equals that one. So, and that's 3 and 4. Well, no, actually 4 is the one that sort of matters. So do 2, 3, and 5 come close to equaling 4? And the answer is yeah, they do actually. 58 and that comes close to 73. So about half of our power is coming this way and the other half is coming that way. So just in rough guessing, I can say, and all of our power, or all the rest of these users are going to equal something a little bit more than this. But in general, my voltage is going to be maybe double that 11.75 or maybe a little bit more. Okay, so it might be call it 12 or 24 or it might be 36. That 36 sounds a little bit high. But in any event, with those values rolled out that far, while we don't necessarily need to round the resistance values because they're probably preferred, probably are going to want to not round our current values. We're probably going to want to carry those out at least to the 4th decimal place, something like that, right? Otherwise, our voltages might be off by quite a bit. You know, if these were rounded out to the 3rd decimal places, I wouldn't necessarily be as concerned, but the fact that they took the what's provided is taken out a little bit further, it doesn't hurt us to be a little bit more precise, right? Okay, it just means writing down a few more numbers. Okay. So let's see. If we do a little bit of math and we add all this up, let's see, 9 and 2 is 11, and 11 and 5 and 58 and 73 is going to be 13. So that's 23 or 2.3 and change. Okay, 2.4, somewhere in there. Let's see, survey says, looking at a few, 2.50. 0717 watts. All right, that wasn't too bad. And that, just in rough guessing, seems about right. If I got 2,000 or 20 or 29, some other bizarre number, okay, I did something wrong. So what else do I know? I do know that all the current that's going through number 1 is current total, right? So if I solve for current total, excuse me, for current 1, I'll have current total. So let's see, what do I do to get to take the voltage and divide it by power? Will that give me current?
Power divided by voltage.
Huh?
Power over voltage.
Oh, it's the other way around. You got to divide power by voltage, not voltage by power. Okay. Well, that's certainly one way of doing it. Plug it all in there, and I should come up with, well, okay, this is almost 1, right? So I'm going to come up with something that's close to the reciprocal of 12, right? What's the reciprocal of 12? 1/12, right? or whatever that is decimally. Survey says several different things. It looks like 0.07835 amps. 1/10 would be 0.1, right? So 1/12 would be a little bit smaller. So that's in the ballpark, right? A little bit less than a tenth. It's an 8%. That's about right. What's 8 times 12? 50 there. Just about, so. All right. Where else can I put that value?
I told
Is it everything that's going through there, IT? So I can now plug that into here, 0.07835, and that's also amps. Now I can get system voltage, can't I? Same thing, 25.0717 divided by 0.1 would be 25, right? Wouldn't it? But it looks like it's something a little bit less than 25. Or excuse me, it's something less than 1 being divided into it. It's going to be a number bigger than 25. Maybe it would be 30, 32, something like that. Survey says, some of you got 31.99999. Some of you picked 32. Okay, 32 volts it is. Well, while I'm at it, I might as well solve for R sub t, right? 32 divided by, again, something slightly less than 1. Wouldn't that be what I use? Take 32 divided by a current. So 32 divided by, or 0.1 would be 320, but it's going to go in there more times than that. So maybe 390, 400, somewhere in there.
408.14.
408, yeah, that's what this person got to. So R sub t, and we knew this one was going to be a little bit bizarre anyways. So 408, 4237. Oops. I can make a 4. It's not easily. 4, 2, 3, 7. Little ohms. Okay. So now, whenever we get done with all of this, instead of doing the powers as our cross check, whenever we sort of get down to where all the resistors are done, we can then come back and do the resistor analysis based on the values we've got and see if that actually adds up to that 408, right? Comes out to that 408. Okay, so we've got a couple of currents, we've got a resistance. We can actually come up with a resistor value for number 1 too, right? 1175 divided by, again, that 0.070 or 07835. Let's see, here it gets us down to 149.9, 149.9, 150. So yeah, a preferred value, the 150 is definitely a preferred value. So that's probably 150. Now mathematically I can't do anything, can I? I'm going to have to do some analysis. I'm going to have to come over here and figure out what the analysis is. So we know that from here, that's 0, and here is 32 volts. And we know we drop 11.75 volts here. So that node right there has got to be the 32 minus the 11.75. And that voltage, whatever that value is, will be felt across 4 and 235. We can't really write it into 235, but we can plug it into 4. Okay. And the advantage of plugging it into 4 is we know that half of the current that's going this way, or some close to half, is going this way, and the other portion is going that way. So that will be useful to us. So we're gonna say 32 minus, 32 minus 11.75 is going to give us, let's see, 21 plus 0.75 gets us 20.25, right?
7.5. Or 2.5, you're right.
Okay, I'll go with it. So 20.25, and we can put that in 4. That's going to be the voltage drop across number 4. Okay, now that I've got that, I can figure out what the branch current is for number 4. Okay, so take our power, 0.73, divided by 20.25, and that gets us a number that better be smaller than 0.07835. If it isn't, either you guys did something wrong, or whoever made the problem did something wrong. So doing that math, survey says it's about half, just kind of about like what we said. So 0.03616 amps. And what's 35 or 36 times 36? 72? Well, that's pretty close to half of that, slightly less than half, which is what we were sort of guessing when we looked at the powers, right? This clump and that, so 2, 3, and 5 add up to being pretty close to 4. So that's still in line, that we're still in the ballpark. So if I now take this value and subtract it from total current coming out of number 1, total current coming out of number 1, subtract the branch that's going this way, whatever's left, according to Kirchhoff, has to leave this node and go through number 2, right? So we can plug in the current for number 2 by doing that math. Subtract this from there, or this from there, don't do it backwards. That gives us a value of 0.0421. Well, that would either round up. Let's go 19. That'll work. Oh, and amps. All right, so now I can calculate both resistance and voltage drop across 2, right? So it looks like 0.04219 divided into 58.728 gives us a value of about 13 volts. We know that whatever is coming across 2 has to be less than this 20, right? Okay. Well, so we can guess that 13 point, this case 92 is a pretty valid number, give or take a little. Seems to be, well, others got a little bit higher, 29, 190, okay. And then taking a very small number, something about like 1/20th, and dropping it into 14 is going to get us a pretty big number. 14 times 20 would be 200, 280, 300 something. Let's see, survey says the answer is 330, 330, well, somebody had 390 there. But yeah, 330 is a preferred value, so this makes sense. 330 ohms. So we're doing pretty good there. Now what do we gotta do? Well, we could solve this one pretty straightforward, mathematically, without doing any more analysis. Take our 20 and divide it by that amount of current. It looks like that gets us to 560, which is a number we recognize as a preferred value. And plug that in. However, to solve for 3 and 5, don't I need to know the voltage drop at the backside of 2? So I'm going to have to take this value, 13.92, 13.92 volts. So I'm going to have to start with 32, subtract my 11.75, then subtract my 13.92 to get to voltage at that node. Still voltage 0 at this node. Okay, but voltage at that node, since I've already done part of the math on 4, can't I just take the 13.92 and subtract it from the 22.5? Okay, or 14 from 22.5 is going to be, what, 625 plus a 0.8 or 62633, something like that? Just throwing it out there really quick. This, yeah, that's what this. Well, we'll put it all over the map. Yeah, there's a 633. I'm going to guess roughly 6.33 volts. And that's going to be dropped across both sides, 3 and 5, isn't it? Because they're parallel. So 6.33 volts here, 6.33 volts here. Okay, now that I know the voltage drop across there, divide those values into the two powers, and I'm going to come up with a couple of currents, which, if I add these two together, they must equal that, right? Okay. Like here we had a 0.028. Call it 7 and 4 amps, 0.01345 amps. 28 and 13 is 31, 41, plus some change, gets you pretty close to 42. Okay? So again, in the ballpark. Also, that's a pretty small number relative to that. Well, it's showing up as a much smaller power. So that's kind of in line with what we thought. So now if I then do my division problems there, looks like we had a 220 ohm resistor here and a 470 ohm resistor here, which also logically makes sense. Pretty large resistor compared to that. You know, one of the questions we might ask ourselves, though, is how come this really big resistor drops so much more power? That doesn't seem right. Well, but the truth is, because the voltage drop across it was much higher than the voltage drop across these other two. Okay. So ultimately, this resistor here, even though those two are pretty close, this one's going to get a lot hotter, isn't it? So one of the things we may have not talked too much about in some of the earlier classes, this one might need to be a 1/4 watt versus that one an 1/8 watt. Actually, up in here at that value, it's probably going to need to be a 1 watt or maybe a 1.5 or 2 watt. Same thing out here. This one, you're definitely going to want it to be a 2 watt resistor, something pretty good size. Okay. And then, of course, we can do our 1/1 formula with 3 and 4 or 3 and 5. Add that to 2. Do the 1/, formula with that combination and 4. Then add that to 1. And it should come out to 408, give or take a little. Right? Okay. Okay. Once again, Mr. Hall, I'm just, man, paper abuse. 2 weeks in a row, man.
That's what happens when you work full time.
I feed it to the shredder and then I try to solve
Hey, when you work at the yard, happens.
it. Okay.
I'm not working at home, I'm not in my house.
All right, so let's look at next week's problem, and then we'll start. Next week's problem is a little bit different. We're gonna up the ante a little bit. Okay, we're going to 6 big bad resistors. And note that we got values all sort of scattered all throughout. Okay, but again, it's doable. Answer what you can. Get to the point that you can't answer things, then start figuring out doing analysis. And then come back and answer what you can. Right? Okay. I know you guys have it. Even though I can't count to 5.
No, that's it.
Alrighty. Oh my, this circuit uses 52 watts. Boy, I really can't count, can I? What's up with that? 52 watts, that's a lot of power. That's like a big light bulb. Okay. All right, let's talk about schematics. And as we talk about the schematics, we're going to talk a little bit about some of the parts. There is no universal guide to schematics. By sheer luck, we happen to follow some plan form that are fairly common. But there is no universal standard or requirement. Let's put this on for you. Oh, let me clean up this mess. It gets sticky in there. So schematics are really, by folly, by whatever engineers decided to do in any given day, schematics have some commonalities that most use, not by requirement, law, mandate, or anything other than that, but there is some desire on the part of an engineer, technical drawer, technical writer, etc., to effectively communicate. So those of us in English-speaking countries choose to use the alphabet, the known English alphabet, because we want to effectively communicate. Well, I think the same thing is true here. However, there are many places where you look at it and you think, well, I sort of get what it was they were thinking, maybe, but they might have been a little, under the influence of something when they came up with that. Okay, so there's a variety of different types of schematics. Most common, the schematic tries to depict the circuit in a very simple form that shows the electrical relationships between parts. it, in all likelihood, doesn't look anything like what you're looking at. Okay? An example of this is those two schematics, the upper one and the lower one. The upper one is before this building was remodeled, the lower one is after the building remodeled. In neither case do they look like the building or anything even closely related to the building. They show all kinds of power distribution. So this is kind of what got taken away, which is actually reflected up here in a very different sort of structure and format. Here's what exists here. If we look closely, I can't see over there, but that circuit should be circuit or control panel. I think that's an I. That's probably reflected. It's reflected right down here, which then comes off a sub panel, main panel all the way across. But nothing here really reflects that you come all the way across the building. Okay, this funny little gray box, a little box right here. It's actually, you can see it's out there. That's that big green box outside David's office. Again, nothing we look at. Oops, sorry about that. Nothing we look at in that schematic gives you a physical sense of what's happening. But it does show the electrical relationships between all the main sub-control panels. Just doesn't show anything beyond that. Well, that's okay. Same thing through here. This little schematic here has got some things there. Let's see, it's got some things there. Well, one of the things it's not doing a very good job of, but it's sort of okay, is it sort of leaves you, well, maybe that's power in. This is sort of clearly ground, or maybe this is power here. Or maybe that's power, hard to say. That could be AC power in here. And then this would be a DC out there, and this is designed to both rectify and voltage drop power. Hard to say. So typically conductors are going to be solid lines. Parts may or may not be symbolic or a combination of symbols. We may also use like a dashed line box to indicate some relation, like all of these, this whole part of the schematic exists in a magic component. Don't necessarily label it, but so they may have a set of diagrams for very specific information, like where all the grounding locations are, or where the power distribution is, or maybe something that helps to identify what all the connectors look like and tells you where they are and what the pinouts are for each of the connectors. The one thing they usually won't do is put everything on one page. Now, somewhere I used to have a diagram, schematic diagram of the space shuttle, all in one page. And I mean, it was not viewable, not readable. I think what at some point what NASA had laid everything out on a board, so we took a picture of it and then shrunk it down, but it was absolutely, utterly not usable. Okay, you could sort of guess. Well, that's sort of okay. That's going to be kind of audio control, or that you sort of guess what some of the areas were, but it was just not usable. So a third type of schematic may actually give you some drawings or images of various components, just so you can figure out where they are. Okay. How many of you opened the hood of your car and wondered where the wide-angle thunder bearing was? Or something fairly simple like the injectors. Where are they? Well, they got to be on the engine somewhere. Okay. In all likelihood, the injectors are buried down under a ton of plastic and induction manifolds. Okay. They're there, but they're buried. So finding them isn't always easy. schematics may help you do that. So enough said in the sense that one of the things you're gonna have to do with the schematic system is pull it out and spend some time poring over it, trying to figure out what the author was trying to do to convey information to you. That's not something you're gonna just pick up in 4 minutes. You're gonna forget. So I used to do this all the time whenever I got new electrical manuals providing all that. I'd take them home with me one evening, take a new one home and kind of go through it, see what they were doing. Now the good news is, in our industry, the ATA creates some standardizing around schematics, so they tend to group things fairly commonly. That makes our life a little bit easier. But we also will see that in the world of other, manufacturing. Automotive industry is a good example of that. And actually, the automotive industry, one other minor benefit, there's a fairly large company called Fox Valley Publications that they do contract schematic services for the automobile industry. So they just say, okay, Mr. Volvo, take all the electrical components out of one of your cars, or maybe don't even install it in the first place. Take the wiring harnesses and all the components and hook them all up. Turn signal indicator, light bulbs, everything. Put them all together, hook them all up, fold it all up into a box and send it to us. We don't want any information from you. If we need some information, we'll call you back. Can't figure out what a thing is. They then reverse engineer everything they've been given and create the schematics. And throughout every single schematic system, I can recognize a Fox Valley Publication schematic in an instant. They do a really, really good job of laying stuff out in a reasonably logical way. I have no idea how much the manufacturer pays for that, but so there are some, just because of how some industries operate, there are some standards there that make life a whole lot easier. I can tell you though, sometimes it can really lead to some flawed things. So, for example, when you look at that schematic, in the day of that schematic, every wire was accounted for. In the days of these new schematics, they don't account for every wire because the spec calls for like Romex XYZ. So within Romex XYZ, there's 3, 4, 5 wires. So the schematic just calls for that line, and then the electrician's expected to know how to hook it up at either end. The end result of that disconnect is we ended up with one of the sub panels wired to where they had a 20 amp circuit breaker feeding one branch, 20 amp another, 20 amp another, and 20 amp another. So 80 amps going out, and one neutral lead going back. Not a big deal until all of you guys plug something into every one of those circuits. And now I'm dropping 80 amps on a neutral that was only designed for 20 and has no circuit breaker on it, because it's the out leads that have the circuit breaker. And I'm sure, and the problem is because the electrician didn't really understand that what was there didn't follow the same form factor when he started adding new stuff. Some stuff I had to rewire myself, others I let it fry and then told the district it's fried. The power to the lathe was one of them. That one was kind of funny too, because they hired the contract electrician to come out. They said, you got a bunch of wires, it's 440, it blew a bunch of stuff up in there. I saw smoke come out of several of the rockers. And he's like, well, I know the one wire because you identified it's broken, but I can't replace any of the other ones until they stop working. I have to physically see it. So the next day he came back, and somebody, I can't tell you who, had taken all the wires in that Walker conduit and pulled them all out, disconnected them, pulled them all out, laid them across the floor, and hooked them all back up again. And you can see about a dozen of the wires were fried. He walked in, he's looking at it, going, what the hell? What happened? And then he saw all the fried wires, and he figured it out. It's like he started laughing, because that wire is expensive, let me tell you. He started laughing, and then I had to fix it. Okay, so there are some schematics that are painfully, woefully depressing, called truth charts, Venn diagrams, something like that. And the idea here is to say, we're going to help you make decisions. So we're going to say, go to this point, measure these results, voltage, current, something. Then I'm going to give you some scenarios about which way to go, a decision tree. And you're going to measure this value, and it's going to say, if this, go that way, if not that, go this way, and if not that, go this way. And you're going to say, I ain't got any of those. Oh man, now what do I do? When that happens, it's usually because the engineer didn't predict or foresee the possibility. My general sense is if you're dealing with a Model A on anything, that you're going to run into that. But once you get to Model L or Model M, the engineers will have sorted out some of the more common problems, and these little charts will be better. The one big advantage to them is take a schematic of the system, make a Xerox copy of it, a working copy of it, then go back to the truth table, because within the truth table, they'll give you some good values. So they'll say if the voltage is above 12.2, do this. Well, okay, it's good, do that. You can then write in the schematic, here's what it should be, and then write in what you actually measure. So there's some value to be had out of these. Sometimes they're really terrible. We've gotten better and better about them though. Okay. Oftentimes it's one of the things that you guys struggle with the most is you take a measure, but you really don't mentally have a sense of what it ought to be at the 2 points that you're measuring. And if you really don't have a sense of what it ought to be at the 2 points that you're measuring, because it's kind of difficult to say, am I close? Am I even doing the right test? Okay. So there are some common rules that may or may not be universal, but I think within a few groups you can kind of be able to pretty much muddle your way through most schematics with some basic standards. Which you ought to be able to somewhat memorize, and it's not too bad. We've used most of them already. Okay, solid line, that's a wire, it's a conductor. Electrons are going from place A to place B, place Z to place double A, whatever that is. We might indicate some shielding on the wire by a dashed or dotted line that maybe even has a dashed thing to ground, a couple of loops around it. The use of intersections, the convention there is a little difficult. The one on the one with the dot is probably the most common these days. The other ones, I guess, a little bit harder to print. But the idea is, in this particular type, if there isn't a little hop, they come together like that, then there's a connection. There's an electrical connection. Here, I just couldn't draw the drawing without having to come across the line, so I put a little loop over it. That's not used that often. More often, what we do, dot signifies electrical connection. A passover like that doesn't mean anything. The wires just had to be drawn somehow. Okay. In connectorology, you'll see wires leading to some form of gender. And it's always male, female. There is not a universal rule with respect to this, but anytime you define the male side of a connector, you're not referring to the connector, you're referring to the pins. The connector is often reversed. So the male pin will have a hole that the female connector slides into, but the male pins go inside the female pins. Gender is a function of the pins, not the connector, always. Okay? And sometimes connectors, so in this particular case, everybody on this side is male, everybody on the other side is female.
Did you say that the dot is where there's a junction?
So in that middle one there, the dot means an electrical connection.
And so
But the passover just means I had to draw it that way.
Okay, so no electrical connection.
No electrical connection. In the other form a straight crossover is an electrical connection, and the little hop over means it doesn't connect. Again, that latter one, they used to use that a lot in some manuals. I haven't seen it in a while. The dot connection is a lot more universal these days. Okay, resistors. The standard form for that is a zigzag line with sharp corners. Oftentimes we will sort of, for lack of a better word, metaphorically represent loads with the resistor symbol. So if I'm like trying to show a logic flow, and out there is a load, which may be an injector, maybe it could be a bunch of different things, we might use just a resistor symbol to represent the load, even though it isn't necessarily actually a resistor. Could be a heating element, could be, who knows. So in this case, we show some basic 2-wire resistor, power in, current in, current out. They're usually unidirectional. They can go either way. The one up there, up here is an example of a multi-tap resistor. It's actually 2 resistors as strung together in a voltage divider. Okay. So depending on how I set that up, and I could have multiple taps all the way across. So in the proximity of where this sits or where that sits doesn't necessarily infer that these are different values from here to there and there to there. Okay. Same thing, the number of squigglies don't represent anything to do with the actual values. In each of these instances here, that would be the same symbol, even though these are all different resistance values and all different wattage values. Okay, the amount of heat they will dissipate is different quite a bit. The variable resistor or a potentiometer or a rheostat, commonly drawn down below, it's a squiggly, it's the zigzag line with the arrow that shows variability. If the center tap is used, the arrow will have a line coming off of it, so that's your third tap coming off, and it sweeps across. In most cases, when you're using a variable resistor with a little knob to twirl it, it actually is a full potentiometer. It's got all 3 leads. If it's being used as a rheostat, they just leave one disconnected. Okay? Why make 2 different devices when I can just make all the same thing and not connect? All right, capacitors, it's just a couple of plates, a couple of lines representing plates. If the capacitor is polarized because of the nature of the electrolyte that they use in there, and it can also be because of the dielectric, they could have a dielectric with multiple sides to it that behaves differently. They'll then indicate, and it's sort of odd, oftentimes in the diagram they'll indicate which is positive, straight line positive, curved negative, but on the capacitors, they fairly universally identify the negative side with a big band. Well, I can't really see it here, but same thing, the big band right there shows the negative side. Another band shows the negative side of the capacitor. There are, and it's a little hard to see, but if it is polarized, they often will have a different length electrode, somewhat like they do in diodes. But that's not universal. So then other plan forms that might show the canister. Here shows a variable capacitor. These 2 are examples of variable capacitors, where if I take the plates and then I move a dielectric in and out, or I take the plates and they're sort of my fingers are the plates and interweave them together, or separate them, interweave them. In both cases, aren't I playing with proximity? The amount of surface area that's in proximity, so that would change the capacitance value. There are cases where we use those. Back in the day of your old AM/FM radio in the car, you'd twirl the one knob for volume, that was a potentiometer. The other knob that you twirl for tuning was a variable capacitor. Okay, and actually it's a pretty sophisticated one. there's a little gearbox in here, so as you turn the knob, the capacitor actually might only go a quarter of a turn or a half a turn. But you turn that knob a bunch of times, and it's a little gear-driven thing in there. Okay. And by the way, capacitors can also be a part of the circuit board. Okay, I can take and put just a little part of the trace here, and another little part of the trace sort of embedded in the circuit board on the bottoms or on the bottom side, and those are my two plates. But it can happen where you're saying, I'm seeing this schematic, I'm seeing it, but I'm not finding it on the board. And maybe because it's part of the circuit board. Okay, switches. Two forms, and I can't tell you which is more common. The one form doesn't put a dot on the contact. The other form often will put a dot there. Sometimes they'll even put a dot on the throw. But the idea is to imply the ability for that to move. I can also have some switches gang together. If I do, I often put a dashed line between the two to show that I can't independently operate one of them. Okay? They either both go one way or they both go the other way. If I play around with a little kind of a curved thing and a little hat on it, that's actually a circuit breaker that is in general use intended to be both a switch and a circuit breaker. Okay, a circuit breaker switch. I can then have a switch go two different directions. Okay, so I can have one pole that throws two different directions, right? Or I could have two poles, double pole that has a double throw. Okay, so do know there are questions. You got to be able to decipher what does throw mean. Is throw the number of possible circuits or the number of possible directions? Which is which? Guys should have that memorized from DC Electrical. Okay, is this a single pole double throw switch? Or it is a double throw single pole switch?
Double pole, single throw. It's a double throw single pole because it's one circuit.
So the pole represents the potential circuit, and the throw represents the number of directions the circuit can go to. Right? Is that a fair way of doing it? Make sure you got that clear in your head, because there are questions that are going to try to mess with your brain. You're like, oh man, I didn't remember that. What is it? That was the wedge in turn. What did I do to myself? So batteries, usually need to draw a bunch of them. It would be reasonable to presume that means single cell versus 3 cells, but that's not written anywhere. Okay, so it's very, very common. Oftentimes what they'll do is they'll show like 2 or 3 batteries and 2 or 3 power sources, and they'll show fewer blades in there because it's a lower voltage, but it doesn't necessarily tell you what the actual number of cells is. If it's AC, they don't bother with the individual cells, they just use a circle with a squiggly, and it becomes a power source. Antennas, which in and of themselves are power sources and loads, depending on what the radio is doing. So when the radio is transmitting, the antenna becomes a power source outwards. When it's receiving, it becomes a power source inwards to the radio. And obviously on the other side, it's a load. So, but they are definitely a load on the radio. And in fact, one of the worst things you can do to a radio is transmit without the antenna there. Okay? That's like calling upon the light bulb to conduct without the filament. Okay? And letting it try to conduct. Well, it does some arcing instead, right? Okay? So coils aren't too different from a resistor, other than the little squiggly is rounded quite a bit. And it may be done like this, or they may actually do something circular. They're then showing sort of an open air versus it's got a laminate in there, some type of a permeable reluctor in there. Another one will be a multi-tap coil, very common in power supplies. So for those of you with a desktop computer, you have a multi-tap power supply sitting in there, a little transformer. Two wires come in, the two wires from the plug outlet, and then there are multiple taps coming out, 12 volts, negative 12 volts, 5 volts, negative 5 volts. And of course, the preponderance of that, because the computer then needs to go be rectified somewhere after the voltage is set. Another version is they can actually make a variable inductor or coil. You think, well, that's pretty weird. How do they do that? Well, it'd be kind of hard to unwind it and wind it back up and unwind it and wind it back up as you're doing things. But one of the things I could do is this reluctor in here, not reluctor, but laminate in here that tends to concentrate the lines of flux around the coil to make it either stronger or weaker magnet. I could move that in and out of the coil, in the range of the coil, and that would change the amount of inductance it develops. All right. So, again, not commonly used as something that the typical user would use, like the variable capacitor was, but it is used in situations where you, the installer, might be required install the equipment, then attach some special test equipment, and then fine-tune a variable inductor to some correct value or some current value that's applicable to the installation. So you may not know that you're actually tuning an inductor. They may say, pull the little sticker off of here, and there's a hole in there. Stick this screwdriver down in that hole and twirl it one way to get one result, or the other way to get the other result. All right, so now it gets a little difficult. So in solid state devices, we invented a lot of stuff. And in fact, are continuing to invent a lot of stuff. So I'm going to talk about a few of them, but know that even the sky isn't the limit. I don't know what the limit is. They're going to keep inventing more and more of these kinds of devices that do all kinds of different things. But the basic principle is going to be the same throughout all of them. So if you remember, we talked a little bit about the diode, right? Remember we talked about that? We said, if I take some, call it P material, and I take some N material, and in each case I've thrown some electrons or molecules in there, one that has some holes in the outer shell, others that have an extra electron in the outer shell. They'd happily get rid of them if given a little bit of incentive. The other would happily take them if given a little bit of incentive. And if I take the two substrates that are doped with these and bring them together, there'll be an exchange of electrons. Okay, so if I bring these two together, what's going to happen is I'm going to get some negatives here. And then over here, I'm going to get some positives. And they're going to sort of form, and they sit there like that. Here I'm normal, there I'm normal. Here I've got negatively charged ions. There I've got positively charged ion. An ion is something where the number of electrons don't match the number of protons, right? So we're gonna call that the depletion zone. We can then say one of them is an anode and one of them is a cathode. That's a legitimate statement. It's very much like the anode and cathode in a galvanic relationship when you talked about corrosion or about batteries, etc. If I in fact throw some electrons in to one side, the inside, that depletion zone, what'll happen is, if I throw an electron in here, flunk, it'll go into here, and one of these guys will back up a little bit. Throw another electron in, they'll back up and they'll keep backing up, right? At about 0.7 volts if it's silicon or 0.3 volts if it's germanium, this thing will start conducting and electrons coming in and they'll start coming out. Okay, they'll start going. Going the other direction, if I throw electrons in here, the negative static force just starts backing these electrons up. So the depletion zone gets bigger rather than collapsing, right? So we came up with the plan form for this, and we said we're going to make a big arrow. And we're going to draw the arrow. And we're going to say electricity goes this direction. And that's the wall. Okay, only it turns out electricity doesn't go that direction. It goes the other direction. So then we said, okay, holes go this direction. And that's true. All the holes that were being filled like this have now come over to here, haven't they? These are all holes. And as each electron comes, the holes will go the other direction. Okay, we're good. I'm okay. We kind of got to remember that because when we start adding to this device, it's going to get very convoluted. And it's almost as if they were intentional about saying, let's see if we can really confuse everyone and make this totally complicated. But if I take and make this guy positive, or attempt to make this guy positive and this guy negative, electrons are going to travel against the direction of the arrow. So if I put a plus symbol there and a minus symbol there, and I have at least 0.7 volts, it's going to start conducting current. And then remember we talked a little bit about there's some of them that will conduct current the other direction. This actually will conduct current the other direction if I get enough voltage potential. Only it'll do it so suddenly and rapidly that it'll overheat that thing and it'll explode. There are some that are designed to reverse flow above a certain voltage with a relatively controlled cascade effect.
Why on the P side do we have negative? Aren't those the holes on that side?
They were there.
Okay.
They were there. You had a bunch of electrons that were there, or a bunch of holes that were there in the form of those molecules that would like to take an electron, but they don't have to. Because I put this material together, these that would like to give up their electrons did. They all jumped over here.
So hole flow goes that way.
So the holes will go this way. If I take and throw an electron into here, it'll migrate up into here and push one back this way. And once they get to 0.7 volts, they'll actually start jumping across.
Oh, in terms of doping, though, isn't the N material negatively doped, or?
It is, but when I brought the two together, remember, I'm only defining the depletion zone. Everything out here, it has a bunch of extra electron, not extra, but they're not ionized.
Oh, sorry, I thought.
Right?
Okay. Yeah.
So these represent only the ionized atoms. The atoms that actually have an extra electron, one more electron than their proton, or one less electron than their protons. Okay? So the depletion zone only defines those atoms that have been manipulated because it stuck the two materials together. So the diode then reflects is reflected here. We then have a couple of diodes that will behave differently depending on how light affects it, on how you treat it with respect to light. In fact, it turns out all of these silica-based circuits, light will interfere with them. So they're usually, if you don't want light to interfere with them, they're buried in an opaque package, a little black opaque package. The next device that's fairly common is called it's called a light emitting diode. This diode right here, along with the notion of miniaturization, are probably the two most significant advances we've had since this stuff was invented. And in terms of just outright technology. Now, how we've manufactured this stuff is just amazing. But our ability to miniaturize these guys is profound. Our ability to cause a whole bunch of light to come out of one of these guys without inducing any heat is also become profound. Okay? It used to be, when we first invented these guys, a very, very narrow band of light in the electromagnetic spectrum would come out. So they didn't produce a heck of a lot of light, and it was kind of hard to see. And in fact, it was kind of hard to see, so they put a little reflector array in here to get all the light to reflect up in a fairly narrow, tight band. Well, these are only going to be used for indicator lights anyways. So many of you, I'm sure, have seen LEDs where from the side you can't really see them too well. Because, and in the spec sheet, you'll see field of vision, 40 degrees, something like that. However, they put out reasonable light, a reasonable amount of light, given that they're only using 1 or 2 milliamps. Most of these guys typically operate at 1.5 volts, somewhere in there. And it's all the LED ever needs. Usually doesn't need too much. However, what's happened is we've now invented these substrates such that they not only do they put out light in a much wider spectrum, so instead of just a very narrow band of green, we actually get a much wider range of green. So there's a lot more photon energy coming out of there, still without producing the heat. So we did incandescent lights, which produce a ton of heat. You can cook with an incandescent light. Okay, done it many times. One of the best ways to make prime rib. When you have an oven up to 250 degrees, actually about 350 degrees, brown it, turn it back down, or turn the oven off and put a hot lamp in there. Let it sit at about 130, 140 degrees for 8 hours. Oh man, it comes out so tender. It comes out really, really good. So you can do that with an incandescent. No way are you going to do that with a fluorescent light. I won't do it, but I can reach up there and grab it. It's not that hot. The end is going to be a little bit toasty, but it's not that hot. So it's not producing a lot of heat. So it's much more efficient. Okay, it's probably about 1/8 of the power being used for the amount of light being produced from incandescent. They now have a whole bunch of LED based of these lights where I can just take that out, put the new bulb in. In fact, if it's a newer ballast, I don't even have to change that. They're about 10 to 12 times less power for the same amount of light, which makes them 40 or 50 times less power for the same amount of light from the incandescent bulb. Well, if you think about what a stoplight is, how many of you have been up close and personal to a stoplight? Okay, when you see it, it's a little bitty speck out there at the end of the road, right? When you're up close and personal, it's a big bulb. Okay, they're big, they're very big around, and an incandescent, very bright incandescent bulb times all of the different stoplights all over San Diego County. Man, that's a lot of current, 24 hours a day. That's a lot of current, 24 hours. If I can replace all of those bulbs with LED fields and have 30 times less power, man, I have way cut down the power bill. So it might be worth buying all of those. Except, here's the problem. I already went out and got rid of all my incandescent bulbs to put in the little fluorescent curly-Q things, and that are supposed to last forever. And now you're telling me forever hasn't happened. They're still working, but I should throw them away and buy the LED bulbs? No way, I'm Scottish, ain't gonna happen. I'm way too cheap. Right? I'm gonna wait till those puppies wear out before I get the LED ones. You betcha. Actually, the truth is I'm cheap, but it's not so much about that. I know that in the leading edge of technology, making LED light bulbs, they're gonna be really pricey because they know all the yahoos that buy Priuses, or none of you own Priuses right now, all the yahoos that initially buy into some of this technology, okay, they tend to pay a lot more for it. But if you wait a little while and wait till the trailing end of technology, you can get a pretty reasonable price for the exact same thing. Well, we're now just at that threshold where the LED lights are starting to come down. And there's some value to that. On the Zener diode, I think we talked about this before. Remember we talked about this guy. What it does is it says, I'm going to work like a regular diode, 0.7 volts, boom, I'm conducting. Going this way, I'm going to dope this thing a little bit differently. I'm going to throw in the extra molecules a little bit differently so that above some voltage, and I can set these at preferred values. The common one for 12 volt voltage regulators is 5.6 volts because we put it in a voltage divider circuit. And so when this thing starts to conduct, it'll turn that transistor on. Below the value, it won't. Above the value, it will. And then what your load starts getting used. This could be the field coil for your generator. Okay, it's a very simple voltage regulator circuit. So what we're going to say is we'll let electricity go this way at 0.7 volts. Coming this way, we're going to say we're not going to let it go, just like normal, until we get above, in this case I threw out 5.6 volts. Then we're going to start letting current go the other direction. So when I measure, there's a 5.6 volt drop across here. And it's not going to cascade to the degree that so much current happens. Now, if I hit it with 10,000 volts, it would. Okay, there's some upper limit to the amount of current any one of these devices can handle, and they will get hot when they're running current through them. Okay? The double Zener diode is a special breed of this that says our reverse bias voltage and our forward bias voltage are both set. So instead of that 0.7 minimum that we get with most diodes, they'll set whatever the threshold is. So it might be take 0.56 volt or 5.6 volts to go either direction. Okay, there's not many applications for those to get used, but they're there. They're, something's there. So, okay, and that's just a couple of examples of, or 6 examples of diodes. All right, now we're going to change the rules. And we're going to confuse the snot out of you. So we're going to say, let's take 2 diodes and put them together, and we'll share one end of it. So we'll go over here. All right, stretch this out just a little bit. And we're going to put another in region in here. Okay, and in the in region that sits here, we're going to form another depletion zone on this side, and fortunately gravity keeps working throughout all of these experiments, and we'll make a bunch of negatives here. Okay, we're also going to take and put a third lead into the P on this side. Okay, and that's somewhat like what we've got drawn here and drawn here. In one case, that's what we've got over there. I shared the P, put an N on either side. I could also share the N and put a P on either side. Now this particular device will allow us to control the amount of current through a main circuit with a very small amount of current. So instead of being a one-way check valve, it becomes like a gate valve. Okay? It has an advantage over a relay it's wired very much like a relay. And a relay is a very small amount of current, like the master relay. Small amount of current to control that 300 amps that the starter uses. The one significant distinction is the relay, you only have one option, right? On or off. There's no in the middle. Whereas this guy, I can actually use it like a variable resistor. With a very small amount of current, I can let a little bit of current flow through the main pathway, which is what a resistor does, right? So it becomes very much an analog device. So what's going to happen here is, now this particular guy, I've got a little bit of a problem here because I have to make this guy positive. I have to let some of the electrons out, okay, to cause the depletion zones to shrink. So if I take and somewhere up there I've got a positive circuit, I'm going to put my load here, and that's going to go up to plus, right? And then down here we'll go to ground. And then if I start tying this guy to positive and let the negatives out, so if I start making this guy positive and let the electrons start flowing, these depletion zones are going to start shrinking as some electrons will start to flow and follow out. But a whole bunch more will travel all the way across through the load and back up to positive. Okay? And in fact, there'll be what's called a gain value for the transistor. Let's say the gain is 10. So for every one electron that travels this way, 10 are going to travel across that way. Right? Or it's a gain of 20, it would be 20 electrons traveling across. Now, my same rule, this isn't going to work until I get to 0.7 volts silicon, or if it's germanium, 0.3 volts. So I'm going to have to get above some threshold value to get the depletion zones to collapse enough to where things start to conduct. That's a pretty cool tool. So when we go back to what I was talking about in terms of miniaturization, just to help you sort of mentally get this, I could change the load here. Let's make the load a capacitor. Okay. If I turn that thing on enough, I'll charge the capacitor, right? That capacitor will be charged, so we can say that's a 1. Or I can have another part of that circuit that lets the capacitor discharge, or just leave it alone and it will self-discharge. And when it's discharged, it's a 0. Got a 1 and a 0. Okay? That transistor and that capacitor now becomes a memory bit. So how much RAM do you have in your computer, in your iPhone? 64 gigabytes. And there's 8 bits to a byte. So 64 giga times 8, we're up to a yotta already. Right? And that just fits in your iPhone. Now remember, in your iPhone, 70% of what's in there is the battery, a whole bunch of screen. What's actually all the brains and memory and everything is just a little bitty thing to the side. Okay? And one small part of that is that 64 gigabit. Okay, it's a dinky little bitty. I got 64 million, trillion, gillion, whatever that is, a really big number of those transistors and capacitor pairs just to service a memory. Now, the other thing that's going to happen is that capacitor is going to have to discharge because that's what they do. They're not like batteries. Even batteries will self-discharge. So I'm going to have another part of the circuit that comes through and refreshes the state of charge. So all of those that are charged get refreshed. And I might do that like every nanosecond, every trillionth of a second. So you guys might have heard of the term refresh rate. That's what this one, another part of the computer just goes through and says, we know where everybody's at in their at this current instant of time, and we're gonna refresh the charge on all the capacitors that are charged. And a little while later, we're gonna do it again. 7 nanoseconds later, we're gonna do it again. So, but I just went down that rabbit hole a little bit to help you conceptualize how much we have miniaturized.
How do you do that? Like, just like, how do you get all that in there, all that junk in that?
That's the magic, isn't it?
Yeah.
A lot of very, very precise lasers. Just a very small amount of lasers, so they use chemical process to lay out a layer of silica, do doping, layer of insulation, and lasers going through and cutting tracks and cutting out material. It's phenomenal.
Do they use diamonds at all? Is there diamonds or?
They use carbon quite a bit, but they don't need it in the diamond state.
Oh, okay.
The laser, in most cases, they're using fairly high pressure air and lasers, so anything that the laser hits is turned into a gas and blown away. Etching is a little bit too abrupt for to get that fine particulate, but they literally are able to carve a trail of a few molecules in width. I mean, it's phenomenal, the nanotechnology. So here's the rub. One of the things that's going to happen is, when I turn this puppy on, I'm going to have some electrons going this way, and some electrons going this way. And I'm going to have some gain. So let's say I got a gain of 10. So I'm going to have 11 electrons coming in here, 1 electron coming out here, and 10 coming out there. So the two junctions are going to behave a little bit differently. And if I want to introduce sensitivity or other characteristics, I'm going to probably change these two junctions slightly, and how I dope them, and how thick they are, and how the leads are attached. So very quickly, even though logically I should be able to just flip this around and it ought to work the same, I'm going to start playing with these things a little bit such that polarity is going to matter to them. But the polarity vernacular is a little bit wonky. So I'm going to have to come up with some terms. I'm going to have we've already talked about holes and we've already talked about negatives. So I'm going to have to come up with a term that says I've got a collector of either holes or negatives, and I've got an emitter of either holes or negatives. Okay, now if they just stuck with negatives or just stuck with holes, it would have been good. But when they went from one to the other, they changed whether they're talking about negatives or holes. Now the base is the one in the middle that controls. The base is the same. But if you look at the way these things are set up, and this particular diagram right here is actually incorrect, but the arrow rule that we used before with the diode holds true. As long as electricity, the negatives are going to travel against the direction of the arrow or against the direction of the arrow, current will flow if the base is charged enough, either letting electrons out or pushing electrons in to get this thing to turn on. So depending on how I install this, it essentially, with respect to the NPN, because the P is in the middle, I'm going to talk about holes. With respect to holes, in the NPN, the collector will collect holes and emit holes. In the PNP, the middle is in the N, so it collects negatives and emits negatives. That means that in truth, the way it's drawn gets stuck in, with respect to polarity, gets stuck into the circuit backwards. But the arrow won't be there. The arrow, by doing that, that gets the arrow in the correct direction with respect to negative and positive. The difference is what becomes the emitter now becomes the collector, and what becomes what was the collector now becomes the emitter. The base remains the same. A couple of other very important things about PNP and NPNs. For the NPN to work, I've got to have the NPN on the negative side of the load so that as it starts to conduct, what is P remains P. So I've got to take the P and attach it to something positive to get this guy to turn on. If I'm on the positive side of the load, the P will never be more positive than this end of it. So if I want to control on the negative side of things, I kind of got to do it with an NPN. Well, for reasons of, I think, because we already had developed much of our system where you've got positive, the battery, the main human interface, the on-off device, the key switch, the master relay, the whatever, is all on the positive side. And when we turn that switch on, we are not only going to turn on power to the load and controller, but we're going to also turn on power to the computer that's running things over here. Now in this case, I've got it drawn as a variable resistor, but this could be replaced by your electronic ignition control module. Okay? And this could be your igniter coil. And this could be the main transistor that turns it on and off. All of this may be in the computer box. And this is external. We don't really know. So the other thing that's very, very common with PNPs and NPNs is if it's a PNP, I'd put it on the positive side. But for now, we're going to say it's an NPN, and all the computer control will be on the positive side of things. It may have NPNs, PNPs, all kinds of logic gates, or it may be a simple variable resistor. It could be another PNP transistor that's not an opaque package, so that as light hits it, it starts to conduct negative, causing this to go negative, shutting off the light. But as the light goes out, the PNP starts allowing this to go positive, causing this to come on, turning on the light. So it could be a very simple circuit. It could be a variable resistor, something, you know, I don't, this could be the potentiometer in your boom blaster. This here actually isn't a resistor, it's the magnetic coil of your speaker. Okay? Or, and this is what drives it, or maybe this is your iPod right here. iPad, do they still have iPods? Whatever, this is whatever, it's providing a digital signal to control this, which is working the woofer in your car. All kinds of different possibilities there. Almost always, if I just hook the circuit up like I've got over there, there is a possibility that for a period of time, that thing could stay charged, particularly if I've got a capacitor in there or something like that. So almost always, when I hook one of these guys up, I give it a positive connection to the off. And if it's a PNP, that would be, it'd be reversed. But I give it a positive connection to off. So if I have this variable resistor set to where it's at 10,000 ohms, and this is at 1,000 ohms, this is going to be very negative. And so the NPN is, it's going to stay off. Nothing I do is going to turn it on until I start bringing the resistance value down. And once I get the resistance value down to somewhere near here or something below, this is going to start becoming positive. And this guy will start turning on, connecting the load. Okay? This device, with respect to here, is negatively controlled. Right? Controls on the negative side. It's negatively controlled. However, what controls this controller is positive control. That's why it's really, really important for you guys to kind of understand those distinctions. I'm not going to get too deep into anything trying to have you analyze which is the anode or cathode, collector, emitter, base, because it just doesn't. Okay. What I want you to be able to know is the load here, your injector, your fuel injector, your radio, your whatever. The load here will commonly go to a computer device that will have an array of these big output transistors, usually NPNs on the negative side. For you, it's important to know kind of how that works, but at the end of the day, what are you going to do? you're not gonna replace any one of these. You're gonna find out, do I got power going to the load, power coming out of the load? Okay, I got that. I got a computer that's got power and ground, all that's pretty good. And all the signals coming into the computer that tell it to turn on are good, but no output. This isn't connected to ground, so it's gotta be the computer. Or if I found one of the other things wrong, I gotta fix that. One caveat though, every time I think it's the computer, I gotta go back up to here and say, is this load okay? Because if this load has a few internal shorts, I'm now sending more current through this device than it was ever intended to handle. And that may be why it failed. If you don't verify, never, ever, ever replace a computer control without first verifying that the load is in fact providing the appropriate resistance to the circuit. It can be a little wonky, because sometimes it's great when it's cold, but once it warms up, it swells and shorts, and suddenly that internal short that I didn't know existed starts happening again. Okay? You'll just be buying brand new computers all day long. Okay. Let's see, let's do one more slide. So yeah, I've kind of said all this. Don't try to remember it. I remember it because I work with a number of little circuits, but please don't do that to yourself. The bottom line is the little arrow shows you, if the little arrow is pointing from negative to positive, it'll conduct current. In this case, if it's a diode, it'll conduct current, period. If it's a transistor, because I have the opposite junction, I've got to feed it something to get it to conduct. So, and then this slide here, this is just a different kind of transistor, and there's millions of different kinds of transistor. The junction field effect design, what they essentially did is they said, let's make the middle portion, let's make the middle portion a tube around the inner portion that's, in that case, the two ends. So what we're going to do is we're going to take and make this a donut around here. Okay, so now when I fire this up, my depletion zones are a little bit more complex shape, right? But that then allows me to be, in this particular case, what they were trying to do is to get something that was a lot more robust with respect to outside EMF affecting it. It's not necessarily, doesn't work as fast. So it might not be good for high-speed computer applications, but it might be wonderful for where I've got, a major like speaker amplifier, and I've got all kinds of magnetic interference coming off of that speaker. This thing wouldn't be affected by that too much. It wouldn't create too much distortion. Okay? So because it's different, instead of using emitter, collector, and base, they use source, gate, and drain. Are you confused yet? Yeah, I mean, that's the part where I really, in some ways, think engineers went, man, we don't want anybody else to figure this out. We'll just come up with all these really bizarre terms and let everybody sort of be confused. But if you visualize this as an electrically controllable variable resistor, I mean, conceptually how it works makes a lot of sense. And I can use it digitally, on, off, or in an analog manner, a little bit on, a little bit higher, a little bit lower. Okay. All right. So I ran a little bit over. How about we come back at, say, 6:45 till 7?